All right, folks, it's time to head back to some graphing. In this lesson, we're going to talk about graphing exponential functions. We're going to learn about their parent functions and transformations. It's going to be pretty straightforward because it's going to be a rehash of stuff we've already done, just like this always is. That's why learning how to use parent functions is so helpful. Let's start by diving in exponential parent functions. Exponential functions are one of two types of functions that actually have two parents. They live in a two-parent household. So hilarious. Maybe not. But there are actually two parents. There is a exponential growth parent function and there's an exponential decay parent function. The difference between them and in their equation, is that the b part, the base that is raised to a power, if that base is greater than 1, it's an exponential growth function, and it looks like this. It is going up, right? It is raising up. And then an exponential decay function is where if b is between 0 and 1, so it's a fraction, right? It's something less than 1 but greater than 0. It's decaying, so it starts high and goes low. So you notice exponential functions, we've kind of talked about them before a little bit. We've talked about them probably in Algebra 1. Instead of being linear and just being straight, right, they go up curve. They start out slow, and they rise really quickly, right? So their domain on both the growth and decay is all real numbers because they keep going left, they keep going right, so they stay going forever. The range of the parent function. I had some mistakes on a quiz on an Algebra 1 test over a similar topic just the other day. Excuse me. The range on the parent function, not necessarily on the transformed functions, right? If the whole thing gets shifted up, then the range is going to shift up as well. But the range on the parent function is from 0 to infinity. It has an asymptote. What is an asymptote again? That is where the graph gets closer and closer to something, but it never quite touches. So these on the growth function, it's going to start out on the left. It's going to go closer and closer and closer and closer and closer to that y equals 0 line, that x-axis, but it's never going to quite make it. It's going to get closer and closer, though. It's going to keep dividing its fractions. Same thing over here on the decay function. It's going to get in the positive direction. It's going to get closer and closer and closer to 0, but it's never going to quite get there. There is no symmetry on either one. They are not symmetrical at all. So the next thing is transformation. So this works exactly like we've seen. I was going to say half a dozen times, but I think there's only been like 3 times so far. But it works exactly like we've seen several times before. Dilation and reflection is that a variable in the front. So if there's that a not very well, yeah, a variable for now, and it'll be a number when it actually does something, right? That number in front is the one that will either make it vertically stretch, and it works just like we've seen before. If it's greater than 1, or its absolute value is greater than 1, then it stretches, and it vertically stretches higher, and it gets to that infinity quicker. If it is, between 0 and 1, then it's compressed, and it still eventually is going to kick off and do even more, but it's going to go a little bit slower and take just a little bit longer to get there. And then, of course, if it's negative, then the whole thing flips upside down. We're going to see examples of these things here in a minute, right? So now one thing that's kind of weird here is this H, right? The H is that horizontal translation, and just like we've seen before, it goes opposite of expectation because of this negative right there, right? Now, the one tricky thing with this is that H is actually up in the exponent, right? It's up there up top, right? So it's not in parentheses or in the square root, right? It's up in the exponent of the exponential functions. That kind of makes sense. And then the K is just the way it always does. If it's added or subtracted outside, and it does exactly like you'd expect. If K is positive, it shifts the whole thing up. If K is negative, it shifts the whole thing down. Let's look at some examples. Let's pull up a graph and pull up our example. So we want to graph this guy. We want to state the domain and range. So first of all, is this, let's kind of identify some stuff. It doesn't really ask us to do this, but it's going to be helpful as we dive into graphing this. If we kind of can put this in some sort of frame of reference, right? So is this, first of all, is this a growth or decay function? Well, it is, in fact, a growth function, and we know that because 3 is greater than 1, right? It's not like 1/2 to the x. That would be, that should be an x, right? That would be a decay function. Well, I suspect we'll see an example of that. What do you think? So this is going to be growth, so it's going to look something like that, right? Right? Very, very easy peasy. One thing that I didn't mention on both of the parent functions that relates back to going through, on a parabola, on a quadratic function or a square root function, it goes through that 1 point. Well, an exponential, kind of that reference space for where it's up and down. There's not really a vertex, but it's on the parent, on both parents. I noted it on the graph, and I wrote it up here. I just didn't say it, that they both have y-intercepts at 0, 1. So if it shifts up, it's going to be the y-intercept will be at 0, 3, right? Or if it was shifted up 3 or whatever else, right? So let's go back to our example. Oop, we need our graph back on here. There we go. Okay. So it's not vertically translated. Doesn't go up, down. So it's going to go through here. It's going to go through, this basically is a version of the parent function. Now, you notice that I said a version because you have to have a number here, because if it's 1 right here, you have to have a number here that's not 1. It has to be greater than 1, or has to be a fraction that's less than 1 or whatever. Because if it's 1, then the whole thing is just going to be a constant function at y equals 1. And so it's just going to be straight, right? Because 1 to the anything is still just 1, because 1 times 1 times 1 infinity is still just 1, right? And so even the parent functions on the exponential ones, there's variation within. So, but this is basically the parent function. All we really need to do is kind of get a few values. Let's do us a little table of values and pop them in there, and we'll have a graph. So we're going to do x and y. We know kind of what this looks like, right? Because this is basically the parent function, a version of the parent function. And so we know essentially what this looks like. And so we're going to kind of go with our old standbys of -2, -1, 0, 1, and 2. So we plug a -2 in there. Let me grab my calculator. There it is. So we put a -2 in there. We've got 3 to the -2. What is happening? What is that 7? 3 to the, I don't know what I did, to the -2 is 0.111 whatever, 0.1, right? Which, where do I put that on here? Well, it's a number that's kind of close to 0, right? So let's put a -1 in there. And actually that, if we remember our exponent rules, we can just kind of think through what that's going to be. That's going to be 3 to the -1 is going to be 1 over 3, right? So if we're doing it in this decimal form, that would be 0.3 approximately, right? So that's easy peasy. We put a 0 in there. That's also easy peasy because anything to the 0 is 1, and we already actually knew that one right there was going to be 1. We put a 1 in there. 3 to the first is going to be 3. That's easy peasy. 3 squared is going to be 9, right? So now let's plot these points. So -2 and 0.1, so something like that. And -1 and a third is something about like that. 0, 1, we've already got on here. 1 and 3 is right here. And on my graph that I've got, I've only got 8 spaces. So 2, 9 is something like that, right? So this is going to ultimately look something essentially like this. Now this one, I already said, you can see what the domain and range are. This, just like all exponential functions other than specific word problem type situations, the domain is going to be all real numbers, right? The domain is negative infinity to positive infinity. The range, it's getting closer and closer to 0, never getting there, and it's going all the way up to positive infinity. So the range is 0 to infinity. Again, this is really just a version of the parent function. Now you notice that unlike the square root function I didn't mention this on the parent slide, but we'll note it here, that we're not including 0 because it doesn't get down to 0. There's nothing that we can put in this x that'll end up giving us a 0 over here. We get closer and closer and closer and closer to it, the more negative this goes. Negative 30 is going to be like a really small number, right? And so it's going to get closer and closer and closer to 0, but it's never going to quite get there. So it's not including that 0. So it's a round bracket. Let's do another one. I don't know why that happens sometimes. All right, so we're going to graph that and state the domain and range. So what kind of transformations happen? Well, we've got basically the parent function right there, but then we've also got +1 on the outside, so that's that k. So we know that this graph is going to shift up by 1, and so we know, based on that instead of going through 0, 1, it's going to go through 0, 2. That's going to be the y-intercept. We'll kind of prove it with a table, and we're gonna do our same old standbys in this thing. I think that's going to be easy peasy, right? So let's do -2, -1, 0, 1, and 2. Right? So put a -2 in there. Oop. That's weird. 2 to the -2. Get out of our exponent, and +1 equals 1 and a fourth. 1 and a fourth. -1 in there, that one we can do real easy because that's going to be 2, or it's going to flip it over, right? 2 to the -1 is going to be 1 over 2, or 1/2. +1 is 1.5, and we'll write that as a decimal like we did on this other one. Oh, that should be a 5. Don't know what happened there. So 1.5. Put a 0 in there. That's easy peasy. 2 to the 0 is 1. 1 plus 1 is 2, which we already saw, right? Excuse me. And we put a 1 in there. 2 to the first is 2. Plus 1 is 3. 1 and 3. 1, 3. Put a 2 in there. 2 squared is 4. Plus 1 is 5. So 2, 1, 2, 3, 4, 5. Now, the asymptote usually is at the x-axis, or y equals 1. Y equals 0, but the whole thing has been shifted up by 1, which means our asymptote is also going to shift up by 1. I like when the asymptote is not 1, I like to dot in the asymptote just with a dotted line in there, because what has happened? All right, because it just kind of is nice, and you'll see this in college classes and whatever else, where we dash in our asymptotes. It just makes it clearer what we're drawing, especially when we're freehanding stuff. All right, let's go back to this yellow color, and let's do one. No, I'm back up here. -2 and 1 and a fourth. -1 and 1.5. Right, so same idea. It's going to get closer and closer to that 0. This is also, I didn't say out loud and think through the fact that this is a exponential growth function, and we know that because 2 is greater than 1. So we knew that this was going to ultimately look something along those lines, right? Let's do another one. These are easy peasy, right? No big deal. So here's the next one. Now this one's a little bit wilder, right? This time we've got 2 different types of transformations happening. So we got this A on the front, which actually does 2 things, because it's negative as well as being a fraction. It's a fraction, which means it's going to compress. So it's going to vertically compress, pull it down a little, right? And then we've also got up in the exponent, we've got this -2. That's a horizontal shift, right? And that's going to go opposite of what we expect. So this is going to compress. I'm going to kind of make us some notes. Oh, I forgot to state the domain and range of this yellow one. Oops. The domain, oh, yeah, thanks. I know. It's empty, all the things. There you go. The domain is all real numbers. Easy peasy. Negative infinity to positive infinity. The range on this one is going to be 1 to infinity, not including the 1, right? Instead of that 0 to infinity, right? Because it's shifted up, it's going to get closer and closer to 1, but never get there, and it goes all the way up to infinity. Now, back to this guy. Make us some notes. So it's going to compress, which we'll kind of see basically by plotting points, really, because that's how we're going to get that. And it also is going to move to the right 2. It is also, because this 5, that b, is greater than 1, it is an exponential growth function. So it's going to be in this basic shape. So there's kind of some notes on what we expect. So we expect it to shift to the right. So we might want to change our points a little bit. I'm gonna go ahead and do an extra point as well, just because that's going to be easier to see what's happening, right? So let's start at -1 this time, because we know it's going to shift to the right a little bit. So let's do -1 and 0, 1, 2, 3. And I'm going to add an X. Well, actually, I don't know that I'll need an extra one. Let's do that, and let's do those, and we'll see what happens. So let's plug some stuff in here. Now, this is getting a little bit tricky this time, so we'll have to kind of do this in pieces or take some notes or whatever. 5 to the -1 minus 2. -1 minus 2. Let's write this down. Just because it's going to be easier for following along at home, right? So we got -1/2 times 5 to the -1 minus 2, which is -3, right? So that we're going to pop in our calculator. It's going to be a little fraction. Oop, come on, thing. You got this. So 5 to the -3 equals that. And then times 1/2 times -1/2. So it's going to be negative whatever I get out of here. So times 1/2 times, let's just do 0.5. I think it's going to be the easiest way at this point. So 0.004. So pretty small little number, but negative that, right? Oh, that's, I didn't, this is incorrect, right? -0.004, was that right? Yes, it was. 0.04. That wasn't quite right? Because it's not going to open up. It's going to be exponential growth, but it's going to look like this because it's going to open down because of that negative, because it's reflected, right? So it's going to be something like this. So we can go ahead and put this in here, -1 and -0. So really close to 0 at that point, right? Really, really close to 0. Now I put a 0 in there. 0 minus 2, so -1/2 times 5 to the 0 minus 2, which is -2. Right? So let's punch that in our calculator. It's going to be 1/25, but we'll prove it in here. 5 to the -2 equals 0.04, and then times 1/2 times 0.5 equals 0.02. And just to prove that what I said was right earlier, 1 divided by 25 equals 0.04. So 0.02 negative, right? -0.02. So still really close. Really, really close to 0, but not quite there. And we'll notate it by being slightly smaller, right? Little tiny bit smaller. So we're going to put a 1 in there. Now, 1 minus 2. 1 minus 2 is negative 1. So that's just going to flip over. So that's going to be a fifth. So 1 divided by 5. And then times 0.5 equals 0.1, but also negative. Negative 0.1. Negative 0.1. Excuse me. So 2 in there. 2 minus 2 is 0. That one's going to be easy. Because 5 to the 0. 5 to the 0 is 1 times negative 1/2 is negative 1/2. So negative 0.5. So 1 and 0.1, right? So slightly higher. I'm doing a little too much, but you know, get the idea. 2 and negative 1/2. Right, so right there. And then 3, let's put a 3 in there. 3 minus 1 is, as my instincts were good, that we wanted to go ahead and add another number or two in here. I was we can tell that, right? So negative 1/2 times 5 to the 3 minus 2, which is 1. So 5 to the first. So 5 times 1/2. Half of 5, negative half of 5. So negative 2.5. Let's do 4 as well. We might even do 5 just to kind of get our, because it's going to go up slower because of that compression. So kind of getting a better picture here, right? So let's put a 4 in there. So 4 minus 2 is 2. So negative 1/2 times 5 squared. So that's 25 times 1/2, which it's getting late. I don't know. My brain is not braining today. Times 0.5 negative. So negative 12.5. That's great. I think that's plenty. So negative 12.5. So at 4... At 3, I was like, what? How did that? Yeah, because I didn't put 3 and 1, 2.5. And then 4 is negative 12.5, so way the heck down there. So it's going to look something like, whoops, we crossed the 0. That's not what's going to happen. It's going to get closer and closer and closer to 0, but never quite touch it. I'm at an awkward angle here. We can do this, something like that. Right? Something like that. Great. Beautiful. So amazing, right? That's what it looks like. Easy peasy. So let's do another example. See what else can... Oh, our domain and range. Almost forgot again. Kind of out of space. I'm going to erase this junk here and put our domain and range right there. So our domain, again, is all real numbers. It keeps going left forever and to the right forever, right? So negative infinity to positive infinity. Now, remember that we always write an interval. When we do interval notation, we write the lowest number to the highest number. So it's going to go from negative infinity up to 0, right? So negative infinity, we never include infinity. Up to 0, not including 0. Because it never quite gets there. The asymptotes stay the same because there's not any vertical translation. Only a horizontal one, right? Because it's shifted over a little bit, right? You can see it kind of shifted over here, all the things, right? So it's hard to tell because it's also compressed. So like this is where it would normally be right there. Yeah, anyway. Continuing on, that table helps us. All right, so this guy is just kind of a parent function for a exponential decay, right? So this one's really simple. There's no transformations. It's just a exponential decay function, right? So it's gonna look something like this, right? Right? Except drawn better, right? It's going to be something like that. It's not up or down, left or right. Easy peasy. We're just going to jump straight into the table. So X and Y. We'll do all our normal ones because there's no real translation to worry about. So no horizontal translation anyway. -2, negative 1, 0, 1, 2. I realized on that last one, instead of just shifting by 1, I should have shifted by 2, and then we wouldn't have had to do the extra. It's kind of obvious because we were translating by 2. I don't know. It's late for me. It's not actually that late, but I'm tired. It's been a tiring few days. Anyway, let's plug this in here. So we put a negative 2 in here, 1/3 to the negative 2. So 1/3 to the negative 2. 9 even-ish. It's actually 9. That's funny. That's kind of like a weird error in this calculator because it would flip it over and turn it into 3, and 3 squared is 9. So I don't know. It's weird. There's a weird rounding error. I wonder if it does this on the actual calculator, or if this is an emulator issue. That's kind of funny. So it's 9 even is what it actually is. Like a negative 1 in there, that's just going to flip it over and turn it into a 3, right? Easy peasy. Excuse me. Put a 0 in there. Anything to the 0 is 1. Also easy peasy. First is really easy. A third. Put a 2 in there. We're going to square it. So that would be 1/9, right? So that's easy peasy. Negative 2, 9. So right there-ish. Negative 1, 3, which is right there. It's got the same normal y-intercept because it's just a version of the parent function. 1 and 1/3, which is about right there. 2 and 1/9, which is about right there. Easy peasy, straight up, simple exponential decay. No big deal. Whoops. Good enough. Right? There he is. Oh, did I put the domain and range on the last one? I did. Purple and green, right. At least they're in theme, so they kind of look good together, right? So the domain of this, just like all of these has been, is negative infinity to positive infinity. The range is just like the parent, because this is a parent, 0 to infinity. Easy peasy. One more, and then we're done. All right, now we got all kinds of things happening. We got a vertical stretch. This is an exponential decay, so it's going to be in this shape. We've also got it shifted to the left 3 and down 1, right? So since we shifted to the left 3 units, we're going to do our table like normal, right? We're going to do our table, but we're going to pick different values because we shifted to the left 3. So instead of starting at negative 2, we're going to start 3 more than that. So how about negative 5, negative 4, negative 3, negative 2, 1, 0 to get that y-intercept in there. You don't have to just do this, but if you don't shift your numbers when it's shifted horizontally, in order to get a good picture of what you're doing, you're probably going to have to end up plotting more points, right? All right, so that's just kind of pro tip right there. So let's start doing this. We're going to do kind of cheat sheet like we did on the other one that's got all kinds of things going on. So we're going to do 2 times 1/4 to the negative 5 plus 3, which would be negative 2, right? And then minus 1, right? So grab that, please. Thank you. All right. So 1/4 to the negative 2. So it's going to be 4 squared. So it should be 8. Let me prove that that's true. 0.25 to the negative 2. What did I just say? Oh, 4 squared, which is, I told you I was tired. I'm glad I proved it to you because 4 squared isn't 8, it's 16. 16 times 2 minus 1 equals 31. 31 vertically stretched, right? So that's like way up yonder. -4, we're going to put in there. So 2 times 1/4. -4 plus 3 is -1 minus 1. So that's just 1/4 flipped over, which is, of course, 4. That one's easy. This one may be able to do in our heads. 4 times 2 is 8. Minus 1 is 7. That's good. 1, 2, 3, 4, and 7. That big old jump, that's classic exponential function. Big old jump from 31 to 7, right? Big old jump. We're sliding down that hill in a hurry, right? Let's plug in a -3 in there. So 2 times 1/4 to the -3. So -3 plus 3 is 0. That's easy peasy, right? Anything to 0 is 1. 1 times 2 is 2. 2 minus 1 is 1. No big deal. Let's do another one. 2 to the 1/4. Plug in -2. -2 plus 3 is 1. Right? Then minus 1. So 1/4 times 2 is 1/2. Right? 1/2 minus 1 is -1/2. Is that right? 1/2 minus 1 is -1/2. That doesn't seem right. Time out. I'll be back. What did I do wrong? Oh, nothing. Nothing. Didn't do anything. This is vertically shifted down 1. We're doing great. It's going to be okay. Yeah. Anyway, so 2 times 1. What is that? 1/4 to the 1 plus 3, which is 4. So minus 1. That's going to be a big old small number. 1/4 to the 4. So 0.25 to the 4 equals that 256 times 2 equals that minus 1. So negative almost 1. Negative 0.99. Right, it's going to be even closer. This is going to be even closer to -1, but just to prove that that's true. 2 to the 1/4, 2 1/4, and then we'll plug a 0 in there. 0 plus 3 is 3. So that 16 is that 1/64th? I think so. Let's see. 0.25 to the 3rd equals that 1/64th. Yep, that's what I said. Times 2 equals that minus 1 equals -9 0.97. -0.97. Which is not, in fact, closer to -1. What's the error? Be back in 2 seconds. So you probably got it a while back. My counting went weird. That should have been a -1. So let's do that one real quick. -1. So -1 plus 3 is 2. So 2 to the 1, times 1/4 to the, what was it? -1 squared minus 1. So I thought 1/16th in my head. I think that's why I kind of stuttered through the 1/64th. 1/16th. So 0.25, just so it's in the calculator, to the 0.25 squared, which is that, which just because proof, times 2 equal or minus 1 equals that, which, now we can see if we put this in the correct place and we switch both of these, we're getting closer and closer to -1. And we have, negative 0.88, right? Is that right? 8, yeah. Okay, great. That was wonderful. Done did it. So negative 4, 7, negative 3, 1. Negative 3, 1. We're already dropped all the way down in here. Now we're going, our asymptote is down here. We can go ahead and dot that in real quick. Let me dot in our new asymptote at negative 1 down there. And then negative 2, 1/2. 2, negative 1/2. And then negative 1, negative 0.8, and 0.97, and then even closer, and we just get closer and closer. There we go. Look how fast that drops. Like a rock. Chevy depreciation, drop, depreciates like a rock. Ford found on road dead, whatever dumb things you could say about any car brand. Who the heck cares? That's it for that lesson. I will see y'all in the next one. Goodbye. See you later. Have a great, great day. All the things. Bye-bye.